My name is Mark Buckley. I'm on the board of directors of the REMADE Institute, and I have the great pleasure of introducing our next speaker, John Warner. Many of you know John as the father of green chemistry for his work as one of the founders of green chemistry as a movement. While I'm sure he'd shy away from such an accolade, we all know that it's very much true, very much deserved. John is a chemist, an educator, an entrepreneur, and he's worked in industry for nearly a decade as a researcher at Polaroid Corporation, before working at various positions at University of Massachusetts in Boston and Lowell. John is co-founder and president and chief technology officer of Warner Babcock Institute for Green Chemistry. He is also a co-founder and president of Beyond Benign, which provides educators with tools, training, and support to make green chemistry an integral part of chemistry education. He is the recipient of many, many honors and medals, but the one I think he's most proud of is the 2014 Perkins Medal, which is acknowledged as the highest honor in American industrial chemistry. John is also a serial entrepreneur with over 350 patents, 25 licensed technologies to global companies, and started 6 businesses. And we're only scratching the surface, obviously. So please join me in welcoming John Warner. Thank you very much.
I'm not looking at text messages. I have a timer here to make sure that I don't go over time. It's a pleasure to be here in this amazing hall. The Presidential Green Chemistry Challenge Award started in 1996, and for the first 20 years the awards were here, and so it's nice to come home to this. I am trying to figure out what best to say in a day like today, and to congratulate REMADE and the Ellen MacArthur Foundation and all the other supporters that are helping make these things happen. You know, it's interesting, we have a lot of approaches that we can follow for a sustainable future. There's responsible care, there's safe and sustainable by design, resilience, systems thinking, limits to growth, sustainable SDGs, circular economy, biomimicry, ecology of commerce, cradle to cradle, planetary boundaries, green good. There's so many of these things. What makes me sad is we're in such a polarized world that, you know, we always hear, you know, oh, this is the correct approach and this is the incorrect approach. And I go, man, you know, the world has so many problems. We need a diverse set of approaches. And we humans are a diverse species. We also need to embrace that. So if somebody finds one of these approaches works for them, what we need to do is mutually find how we can support one another. And so what's most important is we need some kind of an intellectual model. Now, I don't claim to have any gifted insight here. I'm not sharing with you what I presumptuously think is the right way to think. I'm just going to share with you the way I look at things, and maybe it's a little bit useful. You know, we take natural resources, and through extraction, we make molecules and ingredients. Then we take molecules and ingredients, and we synthesize materials and components. And we take those, and we manufacture products. And if we do a really good job, they stay in use and reuse for as long as possible. But inevitably, we're going to have to turn some of those products back into materials and components through mechanical recycling, through an assemble-disassemble system. And then eventually, we're going to have to turn the materials and components through molecular reprocessing back to molecules and ingredients through what I call the materials metabolism. Now we take the molecules and ingredients, and hopefully they degrade into natural resources through regeneration. And of course, then we want to maintain a stable ecosystem. I look at this, I call this the sustainability pendulum. And the sustainability pendulum has the human-built world in the clockwise direction and the natural world in the counterclockwise direction. In that intersection on the bottom, oh, my watch doesn't get it. That intersection on the bottom is really a quantifiable assessment of sustainability by whichever way you'd like to do it. But what's really important is to realize chemistry and material science have been around for, what, a century and a half? Biology has been at it for over 3.8 billion years of natural evolution. So let's look at each of these 5 systems really quickly as a natural and a human-built way. So products, a termite mound. These things are so extensive they can be seen by satellites, and they last for well over a century past when the termites have left them. Okay, there are less durable goods like beehives and things like that, or a hermit crab. The hermit crab didn't build that shell. It goes into that shell, and when it gets bigger, it leaves that shell, goes to another one. It uses and reuses those products. We humans, we make durable goods like car bumpers and playground pots, or we'll make cups and things like that that we want to reuse over and over again. The hallmark to this system, we need to think about from a technical perspective, is we want to maintain the structural form, and we want to maintain the chemistry. As long as we can do that, we can stay in this loop forever. However, there's this thing called entropy. Inevitably, something is going to happen. When that happens, we must go counterclockwise on the pendulum to the next station, the assemble and disassemble system. In nature, a bird will pick up twigs and leaves and branches and build a nest. We'll have the eggs, the chicks will go out. Interestingly enough, the next time the birds need the nest, they may make it in the same place, but they won't use that nest. They'll throw it all out, and then go around, and they very well may pick up the exact same stuff, but they insist on assembling and disassembling that product. Nature is filled with that requirement of assembly and disassembly. We humans, what do? We make plastic objects, cups and bowls. We injection mold them, and then we break them into pellets, and then we injection mold a bowl and a cup, and we inject them in mold. Or in the paper industry, we have a sheet of paper. We grind it into pulp, and then we make a sheet again. So in the same way, we have the hallmark of this system here is that we allow the structural form to change, but we still want to maintain the chemistry. And as long as we maintain the chemistry, we can stay in this system for as long as possible. However, there is this thing called entropy, and inevitably, every time we mechanically recycle something, every time we repulp paper or something, inevitable that we're going to do chemistry. We're going to break polymer chains, we're going to break fibers, and ultimately we lose those mechanical properties. At that moment, we must go counterclockwise to the next station in the pendulum, the materials metabolism. This is my favorite. This is where I spend most of my time. These cats exist in my house. They're the nemesis of my life. Okay, these cats, I won't go into it. But anyways, they eat. All right, and they eat, and they eat, and they eat. And what happens when a cat eats? They take large molecules and through a process called catabolism, get it? They make small molecules. They turn proteins into amino acids, carbohydrates into sugars, fats into lipids. But that's not all. Think about us. When we ate our lunch today, we're eating the food. We're doing the same kind of deconstruction of molecules. But at the same time, we're growing hair, we're growing fingernails, we're growing blood cells. Nature simultaneously deconstructs and reconstructs at the same time in the same place. We humans, we can't even touch that kind of thinking right now because this correlation with catabolism and anabolism, which equals metabolism, nature has coupled energy. Food is fuel. So this magic molecule, ATP, if you think about it in biology, every time a process releases energy, we stick phosphate groups together and we charge our molecular batteries. When we need energy, we pop those phosphate groups off and we get this. So nature not only couples molecularity, but the energetics of transformation so that it can allow this successful thing. And we humans, we have not even begun to imagine systems like that. Now let's go down here. The cool thing is, of course, that there are no degrees of freedom, right? You've got structural form, you've got chemistry, all no holds barred. So that's kind of fun. Now, if we go down the natural side here, we go, we know beavers cut down trees and make dams. Bees will extract pollen to do things. Nature has an abundant set of regenerative models here. Humans, no, not so much. Our logging industry, our mining industry, our petroleum industry. I am super optimistic. I believe we could learn from nature and we could create better systems. We just don't do it now, and it's a long way away, if at all possible. All right, and then finally, close your eyes, go to your happy place. We all kind of know what we mean by stable ecosystems. All right, now, This final map here, I'm a member of the Club of Rome, and we think a lot about systems thinking. Actually, Donella Meadows, back in the early 70s, wrote the initial book, Thinking in Systems. I feel we lack humility when we do systems maps. We really need to really carefully consider the impact of our mapping, because it's not the things we leave on the map that are going to come back to haunt us. It's the things that we forget to put on the map. You know, because all of these processes here, inevitably there's going to be leakage. And that leakage gets out into the environment and creates a porosity in that intersection, and we lose even more sustainability. You know, when people draw these maps and they have a thing, let's create a map of what we need, we've got to be really careful, because if we define a roadmap by today's state of knowledge, we could inadvertently inhibit the very innovation we need by defining today's state as the state that describes the future. So you don't usually see people drawing maps, saying, oh, every once in a while we'll have an oil spill. Yeah, that fits right there on the map. And, oh, every once in a while we'll have plastics show up on the shore, or in Ohio, hey, every once in a while a train is going to derail and do all kinds of bad things, or CO2 is going to be out. For some reason, these things don't fall on the map. So as we invent and design, yes, we should be looking at our maps and our systems, and we should invent to do that, but we should morally and ethically, and I would add financially, also think about the things that don't fit on that map. So the leakage also is going to come back to haunt us. All right? And so when we look at this, going clockwise, we need to create technologies to help humans adopt behaviors that can be more sustainable. At the same time, we have to invent technologies that are more consistent with life processes and being harmony. Again, in our polarized world, should we have bioeconomy? Should we have recycled systems? The U.S. government, we have BioMade and we have REMADE. They're two separate organizations. We need to figure out how these things can work together, because that's truly the future going forward. And so green chemistry kind of works at that apex, okay? And so the green chemistry has been around for quite a while. It's utilization of a set of principles that reduce or eliminate the use or generation of hazardous substances to design, manufacture chemicals and things like that. And here I feel it's not the only job. It's not even the most important job. But green chemistry is the part that the inventive chemist plays in whatever we're doing here. And so the set of principles, the 12 principles of green chemistry, aren't marketing tools. They're really R&D tools to approach how to do this. Because again, here we are in 2023, and very few universities require students to learn anything about mechanisms of degradation, mechanisms of recycling, models of cancer, or endocrine disruptors. How can we ask inventors to invent things if they're never trained to understand them in the first place? So at the end of the day, this is a fundamental chemistry education, material science education issue, okay? And so I'm really proud, this morning, I realized the Department of Energy Secretary Granholm, do you realize when she was governor of Michigan, Michigan was the first state in the United States that had an executive directive promotion of green chemistry for sustainable economic development. That was in 2006. Okay, and so just so wonderful to have her now as the Secretary of Energy to really kind of understand how these things fit together. But what's missing? How can we? I would argue that if everyone woke up tomorrow wanting what we're talking about, we're still about 50, 60, maybe even 70% of the inventions haven't happened yet to enable us to do the things we want. So we really need to also improve how we invent, okay? And so I'm going to tell you this little weird story. There's the land of products, okay? All the stuff we talk about that we buy, we make, we use, we sell. And far, far away, shrouded in mist, there is the land of molecules. And over the years, through plate tectonics, these continents have drifted apart. And the land of products desperately seeks molecules to solve problems for them. But it's too far. They can't reach it. And if they did reach it, they don't even speak the same language. And then the land of molecules is saying, here, take this, but it can't reach, it's too far. And if it made it, they don't speak the same language. We have a massive inefficiency of solving problems, from fundamental research to what people would call applied research. But if you blow away at the shrouded mist, you see that there's actually 3 islands that connect these 2 land masses, okay? And so that the land of infinite products, right next to that is the land of materials properties. And the island of materials properties are tangible things, unmet needs that the customers want: the color, the transparency, the flexibility. They're the consequence of molecular and materials mechanisms. But man, that's still not a molecule. Next to that, the next island is the island of materials mechanisms. These are intermolecular processes between more than one molecule. This is stuff like engineering things, polymer chain mobility, Hansen parameters, things like that. But that's still not a molecule. Next to that is the island of molecular mechanisms. This is stuff within one molecule: van der Waals surface area, hydroxy group positions, ability to aromatize. Now with the molecular mechanisms, we can start talking about molecules. But unfortunately, we don't take this intellectual step to look at this process. We're just really, come on, please, and we need to change. All right? And our very language inhibits us. Okay, we hear about, to jump from these islands, we can use good old-fashioned intuition or AI and machine learning. And to get across the islands, we do experimentation and automation. All right, but what makes me really sad is when someone says, oh, this is fundamental chemistry, and oh, this is applied chemistry. Do you know that chemistry doesn't have awareness that we know of? For chemistry doesn't know what it's doing. That fundamental and applied is the bias being applied by the individual looking at that. And although that sounds silly, think of the profound impact of that. The chemistry is unaware. The very same molecules that are doing something in an academic lab that is being called fundamental is still doing that same stuff in applied. But we get in our way and we start talking about technology push and market pull. All right. Over 120 years ago, Sadie Carnot created the Carnot cycle. For those who don't remember what the Carnot cycle is, it's essentially, if I were to drop an object from a second-story window, boom, and it hits the ground, and I were to harness that energy, the higher the distance, ironically, the less useful work that I'll get out of it. It's lost in entropic loss in the process. If I were to make an infinitesimally gradual plane and have the ball go very, very gradually down, I could harness almost 100% of the useful work. The way to think about this, if I took a snapshot in time of any process, if I can immediately tell the directionality of that process, there is by definition loss. So I think, from my perspective, we make the mistake when we look at any R&D process. If we can tell, snapshot in time, this is a market pull or this is a technology push, there is massive loss. And that we really need to rethink how we look at these processes and not be looking at that way, but see this as a dynamic equilibrium, which requires what I call the materials ecology and the intellectual ecology to superimpose upon each other. Basic research, applied research, development, manufacturing, and the whole circular economy materials loop needs to coexist so that we can, as we learn fundamental mechanisms, we can immediately apply them and pivot and create. Because, man, the world needs us to be far more efficient than we are right now. Okay, and so it's useful to think of this. I've become very crazy about ancestry. Stuff I'm finding I'm not really liking, to be honest with you. It's but that's a different story. But I've spent a lot of time on Ancestry.com. I feel it's really useful to think of molecular ancestry. Okay, so here's a really silly example. Okay, I was just thinking about this the other day. On my desk, there's a pair of scissors. Let's look at these pair of scissors from a circular economy perspective. Okay, first of all, there's that first thing: assemble, disassemble. There are many mechanisms of assembly and disassembly. There is the screw and the nut and the two little pieces. That's a mechanical assembly, okay? And then that's a chemical assembly where we take the plastic handle, we glue it to the pieces of metal, and then there is the ablative shaping from the stainless steel that's cut to make the pieces of metal, and then of course the plastic is going to be a constructive shaping through some injection molding. The cool thing about this system here is fundamentally there's nothing standing in the way to make this not be reversible. Okay, so we got this kind of going okay. All right, and then we think about the stainless steel is made through hematite, chromite, and coal. Okay, we understand metal alloying. The pigmented ABS is going to be from ABS and blue 35. Now, let's think about this a second. Go on this a little bit deeper. The ABS, all right, this isn't a chemistry class, so I'm not going to kill you. But, oh my God, this is all the steps that go into taking the ABS, acrylonitrile, polybutadiene, and styrene, and they are made from these molecules. They are made from these molecules, and ultimately they come from either nitrogen from the air, natural gas, or petroleum. Okay? This is not reversible. All right, we take the blue dye. This gets even more nightmarish unless you're a chemist and you love this stuff. And so here you have all these molecules that this thing is coming from. And again, you have it coming from either from petroleum or from natural gas, or you'll see there's molasses and starch from the bioeconomy and things like this. And then finally, the glue, which is ethylene and butyracrylate, which comes from butyracrylate and ethylene, again, from petroleum. All right, so now we have this last step here. We got these mined materials coming from mines. All right, you've got the biomaterials coming from agriculture. You've got nitrogen being extracted from the air. You've got the petroleum and the natural gas coming from the petroleum industry. And of course, what I left out of here, of course, very critical is water, okay? And so all of this is going here. So how in the world can we change this, okay? When we look at my pendulum here and we look at my white boxes, okay, extraction, we kind of got that, all right? We can improve it, but we got it. All right, synthesis, heaven knows, the field of organic synthesis and material synthesis has been around. Manufacturing, we got models for that. We've got models for mechanical recycling. We've got models for degradation, but we don't have the molecular process, the very stuff that biology has evolved for 3.8 billion years. We aren't touching this. Maybe we call this advanced recycling, which is blow everything up into the smallest pieces. Very inelegant. This is the frontier of molecular sciences. You know, people talk about chemistry and material science being a mature subject, and I laugh. You know, the chemistry is just on the precipice of amazing breakthrough things going on. And as the sphere of chemistry evolves and gets bigger and bigger, we have the diligent hard work of a lot of people trying to define what do we want. All right, we want sustainable chemistry, we want safe chemistry, we want circular chemistry, we want clean chemistry, we want regenerative chemistry. All of these things are nuances that are very important, speak to a right population, to a group of people. They're all important, but what's necessary for us to look at when we look at this is they're defining the destination. The thing about green chemistry is that green chemistry isn't about defining the state we want to be in. It's about changing the very shape of chemistry so that more things go through whatever this is. Because if you think about it, the way I like to explain it, all right, is I have a 10-year-old daughter that speaks, in my mind, perfect English. She can read, she can write, she's amazing, all right? But she's just now taking classes about nouns, verbs, adjectives, adverbs and stuff like that. You'd say, well, wait a minute, why bother? If she's already reading and writing and using nouns and verbs to learn about nouns and verbs, that seems funny. But I would argue she's just mimicking her parents and her environment. When she learns the parts of speech and sentence structure, not only will she be empowered to how she communicates to the outside world, but how she formulates her own thoughts will just get to a much higher level. I would argue that we in chemistry and material science are like my 10-year-old daughter. We want to be sustainable. We want to be toxic. prefer not to die in the lab, okay? And companies, the really smart ones, figured out that if you kill your customer, that's very bad for sales. So we have been trying to do this, but like my 10-year-old daughter, we can't go back to our curriculum and say, when did we learn the parts of speech of sustainability and circularity? When in our education were we taught this? And I'm here to tell you, we don't. And so until we change the way we teach chemistry, if you get a chemistry textbook from 1980 and a chemistry textbook from 2023, I challenge you to find any significant difference in those textbooks. Okay, the field of chemistry has changed, but not the way we teach it. Now, do the same thing for a biology textbook. It's like a different subject. Why has biology evolved and chemistry's got its feet stuck in the mud? Okay, and how are we going to have a sustainable future if we're teaching the way we did in 1980? Okay, and so I'm not a pessimist, I'm a super optimist, because that's the path forward, is people in industry reaching back to academia and sharing some collaborations in a more meaningful way. That's the way we're going to solve these problems, because if it's really hard to imagine the circularity of a pair of scissors, what are we going to do with solar panels and electronics and automobiles, okay? We've got a long way to go, but man, we can do it because of REMADE, because of the Ellen MacArthur Foundation, and the super optimistic. But we need to look at the fundamentals of chemistry and start questioning, is our toolbox the right toolbox? If we try to solve the problems with the same toolbox, ain't going to happen. So we need to reinvent that toolbox. So thank you very much for giving me an opportunity to speak with you. Thank you.
Thanks again, John, for that great talk. We loved having you at our member meeting last fall, and today was equally insightful.